Okay, this is section 2.3 from James Stewart Calculus Early Transcendentals book, and we are going to go over calculating limits using the limit laws. What you see before you are the limit laws for the limit of a function as x approaches a, and given another function, the limit as x approaches a of g of x. So the very first one is the limit of a sum is the sum of the limits. The second one, the limit of a difference, is the difference of the limits. And the third one is the limit of a constant times a function is the constant times the limit of a function. And the fourth one is the limit of a product is the product of the limits. And the fifth one is the limit of a quotient is equal to the quotient of the limits, provided that the limit of the denominator is not equal to 0. We'll have to do some analysis when that happens. Okay, so in just applying these laws, we can go over a couple of examples here. So in A, or looking at the graph here on the left-hand side, the function f is in pink, and the function g is in blue. And in using the limit laws, we know that the limit of a difference is equal to the difference of the limits. So we have, just to calculate what is the limit as x approaches 2, that is a two-sided limit. And where is 2? 2 is here, that's x equal to 2. And what are the function outputs on f of x approaching? So if I go in, and as x here is approaching from the left, we have our function outputs approaching something that looks like 1.5. And from the right-hand side, we have that our function outputs are approaching 1.5 as well. So we can say that the limit as x approaches 2 of f of x is equal to 1.5. And doing the same thing with the g of x, here's x equal to 2, and now I'm going to the blue graph, and the function outputs as x approaches 2 from the left looks like 0. And what are the function outputs of g of x as x approaches 2? It looks like their output is also equal to 0. So we have 1.5 minus 0, and so this limit in part A would be 1.5. Good. Limit as x approaches 1 of 2 times f of x. This is going to equal 2 times the limit as x approaches 1 of f of x. And looking where x is equal to 1, we're going to our graph of f of x, and what are the function outputs tending towards as x approaches 1 from the left, and what are the function outputs as x approaches 1 from the right. They're equal, and it looks like it's going to be the value of 2. So this is going to equal 2 times that limit 2, which is going to equal 4. Good. Next, the limit of a quotient is the quotient of the limits. So this would be the limit as x approaches 2 of f of x over the limit as x approaches 2 of g of x. And looking where x is equal to 2, we saw from part 1 that this was going to 1.5. And in part 2, we have that it is actually equal to 0. And we will want to, because the limit from, and this is going to be does not exist. And the reason being is that as x is approaching 2 from the left, it's going to approach a value of 0 from negative values, but on the right-hand side, it is approaching 0 from positive values. And so if we take that quotient, we're going to end up with an asymptote, but on the left-hand side, that quotient will be going to negative infinity, and on the right-hand side, it will be going to positive infinity, and so the two-sided limit will not exist because they're not going to the same infinities. So that's the type of analysis that you will have to make in limits of quotients. All three of those values does not exist. Negative infinity does not exist as a limit, and positive infinity does not exist as a limit. All right, moving forward with the limit of a product is going to be the product of the limits. And so we have limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. And we saw from part B that the limit as x approaches 1 of f of x is equal to 2. And now what is the limit of g of x as x approaches 1? Well, as x approaches 1, that is still a two-sided limit. And if we go to the graph, here is where x is equal to 1, and the limit from the right is equal to minus 1, but the limit as x approaches from the left is equal to minus 2, and so this is an undefined or does not exist limit, and 2 times that undefined is also a does not exist. Hopefully that is helpful in applying the limit laws given the graph of a function. We also have more limit laws here. We have that the limit of as x approaches a of a function to a power is the limit of that function to that power. So it's almost like we can just put the limit on the inside. We also have a couple of very important ones. The limit of a constant is the constant, and the limit as x approaches a of x is actually equal to a. Okay. We also have the limit as x approaches a of x to the n is going to be a to the n, where n is any positive integer. And the similar limit, if we've got a radical, we can put our limit inside the radical. And so our nth root of x limit as x approaches a is going to be the nth root of a. Okay. So let's practice with some of these using all of those limit laws. And in general, what you want to do is go ahead and plug in the value of a that you have, and in this case we have minus 8. So this is going to equal 8 squared minus 2 times 8 plus 1, whatever that is, right? So 64 minus 16 is going to give me 8, 48, and then plus 1 is going to give me 49. Good. In this instance, this is going to give me the square root of 2 times 2 minus 1 over 2 squared plus 1, and that's going to give me square root of 3 over 5. And you can leave it at the calculus level. You can choose to rationalize your denominator or not, but in this case, just to save time, I'm not going to rationalize my denominator. All right. Because polynomials are smooth, rounded curves, which we will verify later on in another section, the limit as x approaches a of a polynomial is going to equal the polynomial at that value of a. So it will equal f of a as what we just did. So that is your first approach in calculating limits, is to go ahead and plug in the number that you have into the expression that you have. Okay. We also have other techniques. If f of x equals g of x at all points, except maybe at x equal to a, then the limit as x approaches a of f of x will also equal the limit as x approaches a of g of x, provided that that limit does exist. All right, so here we have a piecewise defined function. For x not equal to 1, we have the function x plus 1, and for x equal to 1, we have the function output is equal to 3. So what is the limit as x approaches 1? So we have, if we graph our function, I'll make these axes this way just for the sake. And what does our graph look like? We have at 1, and we would go up 1 and over 1, up 1 and over 1, and we would have this graph. But at 1, we would have a hole here at x equal to 2, but we would have the function output is 3. So that would be the graph of this piecewise defined function. It still is a function because it passes the vertical line test. So we do have that f of 1 is equal to 3, but the limit as x approaches 1 of f of x is going to be the function outputs. So if we go to the graph, the limit as x approaches 1 from the left is going to equal 2, and the limit as x approaches 1 from the right is also going to equal 2, and so the limit here is going to equal 2. Okay? Here it says we will also use this theorem when a function has a hole or is undefined. When tackling these limits, a 0 over 0 will occur when evaluating the limit, although there are other types of undefined values we will encounter. This requires us to use an algebraic manipulation to unravel the limit. So in other words, remember, whenever we have the limit as x approaches a of f of x, we do want to try f of a, and if it exists, it equals the limit. Okay, so that's our first approach. But if f of a equals a 0 over 0, or an infinity over an infinity, as we'll see later on, or a number where n is not equal to 0 over 0, we'll have to analyze. Or manipulate. Okay? All right, so find the following limits if they exist. So looking at A, this is an example of if I tried to do the limit as x approaches 1 of x squared minus 1 over x minus 1. If I went to plug in the values, I get 1 squared minus 1 over 1 minus 1, which would be 0 over 0. That tells me that x equal to 1 or x minus 1 is going to be a factor of the numerator and the denominator. So I actually start to manipulate that, and I factor the numerator. X squared minus 1 factors to x minus 1 times x plus 1, and in the denominator we still have x minus 1. And now I can cancel my x minus 1s, and this is going to equal the limit as x approaches 1 of x plus 1, and now I begin again, and this I go to evaluate, and that's going to go to 1 plus 1, which is 2. So remember, wherever I have my x, I'm going to substitute that value and try to evaluate. And this is a general technique that you want to make. If you have 0 over 0, then you'll want to factor out that x minus a. Okay. It also, just to be clear here, with x squared, the function x squared, f of x equal to x squared minus 1 over x minus 1 is equivalent to x plus 1 at all points except x equal to 1. So you can't have x equal to 1 in f of x. The way that it is written, it is telling you that x equal to 1 doesn't have an output. And in this case, because we were able to remove it, x equal to 1 is a hole in the graph. So your f of x would look like x plus 1, except at 1 we would go up and we would make a hole. Oh, made a mistake there. We would just go in and do we'd have a hole in the graph at that point. Good. But it agrees at all other points with x plus 1, and so the limits are going to be equivalent. Good. All right. We can do another one. This one in part C is a little interesting, as well as part B. Maybe we'll do part B first. So if I were to just increase or add another page here, I can take this expression and I'll copy it down to here. I didn't. I thought I had copied it here. I'm going to do it again. Copy. And then paste. Alright. So, if I were to follow the approach of whatever h is, as limit as h goes to 0, wherever h is, I'm going to substitute the value of 0. And I notice that I get 4 minus 4 over 0, which is 0 over 0. So that tells me algebraically manipulate. So how can I algebraically manipulate this expression? I'm going to want to be able to factor out the h. So I'm going to, just like with our difference quotients, I'm going to simplify the numerator. And in simplifying the numerator, I end up with 2 plus h times 2 plus h minus 4 over h. This is going to equal the limit as x goes to 0, or h goes to 0, of, if I expand that polynomial, I get 4 plus 4h plus h squared minus 4 over h. And I notice that I can cancel 4 minus 4 becomes 0, and now I can factor out the h from the numerator, and I get h times 4 plus h all over h, and I'm able to cancel the h's, and now I have a limit as h goes to 0 of 4 plus h, and that's going to 4 plus 0, which is 4, and that is our answer. Good. How would you, with part C up here, if you ever have radicals and you want to get rid of that radical, you might want to multiply on the top and bottom by conjugates. So in taking a look at this one, if I substituted 0, I would end up with the square root of 4 plus 0 minus 2 over 0. And this would be square root of 4 minus 2 over 0, which is going to 0 over 0. So I'm going to want to algebraically manipulate my expression, and I'm going to use the idea of difference of squares. We know that if we have a minus b, and if I were to multiply by a plus b, I would end up with a squared minus b squared. And you'll quickly see the motivation for that in a second. So I want to, in my expression, multiply by the square root of 4 plus h plus 2 over the square root of 4 plus h plus 2, because you always have to multiply by 1 so that you don't change the value of your limit. And then I'm going to multiply the numerators, and I get the square root of 4 plus h squared, take away 2 squared, all over, and I just multiply the denominators, and we still have h times the square root of 4 plus h plus 2. And now I'm going to simplify. Square root 2 times square root 2 is 2. Square root 3 times square root 3 is 3. So Square root 4 plus h times square root 4 plus h is just going to be 4 plus h, and 2 squared is 4, and I have h times the square root of 4 plus h plus 2 in the denominator. I find that 4 minus 4 is 0, and I'm going to get to cancel my h's in a second, and I have h times the square root of 4 plus h plus 2 in the denominator, and I see that I can cancel my factors of h, and now this limit as h goes to 0 of 1 over the square root of 4 plus h plus 2, I can plug in my 0 here, and I'm going to get square root of 4 plus 0 plus 2, which is going to go to 2 plus 2, which is 4, and we get 1/4 as our answer. That's a little bit tricky, but that's a good technique to have. All right. I'm going to stop here, and I might do another video so that this is a short one. And I will be back. So this is section 2.3, part 1.